In section 16.13, we'll examine the rules for drawing diels-alder reaction. So let's start with the diene. So as I talked about before, the diene must be able to adopt the S-cis conformation. Now there's an explanation for this that uses molecular orbitals that's kind of more advanced than this. So if you want to go to an advanced organic chemistry text, you can find that and you can see why the things react the way that they do. But for now, we're just going to accept that it has to have an S-cis conformation. So for cyclic molecules, that can still work, depending on their shape where the alkenes are. So if I look at cyclopentadiene, you can see that the diene is already in the S-cis conformation. And in fact, if we want to react it then, a lot of times what we'll do is we'll turn it on its side. And so this is just sort of a three-dimensional picture of it. And we'll take this carbon that's at the top here, kind of bend it up out of the way. So we'll kind of bend it up like that. And then bring it next to an alkene, whatever our dienophile is. This molecule and this are the same thing. I just took this carbon here and bent it up out of the plane so that I can form my new ring with my diene and my dienophile. These type of molecules actually are very reactive because they're always S-cis. So cyclopentadiene is actually very reactive for a diels-alder reaction because it's always held in the S-cis conformation. And as much as it seems weird to draw this carbon bent up out of the way like that, it's actually not that difficult for the molecule to do. However, you can have other cyclic compounds that are always S-trans. So if I have this diene, because of this bridged carbon here, there's no way for this to rotate. There's no way to form S-cis. This molecule cannot form S-cis conformation at all, so it's completely unreactive to diels-alder reaction. And for the dienophile, you need to have electron withdrawing substituents on the dienophile to increase the reaction rate. So you might have noticed that with some of the things I've been drawing. If I just have ethylene, it's actually not very reactive towards a diels-alder reaction. I usually want something nearby that's electron withdrawing. So electron withdrawing things are quite often things with a carbonyl on them. So that could be an aldehyde, could be a ketone, could be an ester, could be anything usually with pi bonds will be electron withdrawing substituents, and all of those things draw electron density away from the alkene, and that makes it a lot more reactive for your diene, because if you remember, the first step of this reaction always is one of these electron pairs from the diene is attacking the alkene. So if the alkene is a little electron poor because there's electrons being pulled away from it, it's going to be more reactive to the diene. Another way to look at that is to look at the resonance forms that you can draw. So here's a resonance form that I can draw, which actually places a positive charge on one of the carbon of the dienophile. So once again, it's going to be more reactive to the diene, since the diene wants to donate electrons. The diene is the nucleophile in this reaction, and the dienophile is the electrophile. So it's going to be more positive, it's going to be more able to accept electrons from the diene, and then more able to do a diels-alder reaction. Okay, if we want to look at stereospecificity of the diels-alder reaction, what happens is that the stereochemistry of the dienophile is retained in the diels-alder product. So to look at that and to see how that works, let's take a couple different examples. One where we have a Z alkene with two groups on the same side. So if I have this do the diels-alder, what turns out is that my two groups that were on the same side of the alkene are either both up on the same side of the product or are both down. You can draw it either way. And actually in this case, this molecule is meso, so it doesn't make any difference how you draw it, because there's a plane of symmetry through the middle, right through here. Plane of symmetry right through there. If they're on the same side of the dienophile, they end up on the same side in the product, either both up or both down. So if they're on opposite sides in the dienophile, hopefully you would guess that they will be on opposite sides in the product. One up, one down. Now these two products are going to be enantiomers, because there's not a plane of symmetry. So you're going to get a racemic mixture of enantiomers. The stereospecificity part is that whatever you start with here, if they're both on the same side here, you get 100% of them both on the same side in the product. You don't get any of the switching ones where you get one up and one down. If they're on opposite sides here, you get 100% where they're on opposite sides of the product. You don't get any of the one where they're both up or both down. So that's how this reaction is stereospecific. And the explanation for this is, again, gets back to molecular orbital theory and how the molecular orbitals interact of the diene and the dienophile. In section 1614, we'll start to look at the retrosynthetic analysis of diels-alder products. Hopefully you can already imagine that diels-alder reaction, because it creates new six-membered rings, is a really powerful tool in synthesis of molecules. So if you want to look at a product and figure out how the diels-alder reaction was used to form that product, or could be used to form that product, the first thing you need to do is locate a new six-membered ring that was formed that could have had an alkene in it. Secondly, you need to draw 3 arrows to reverse the original mechanism, and then reform the diene and the dienophile, preserving the stereochemistry. So for example, we have this dialdehyde, and we want to go backwards and try to find the diene and the dienophile. So all you do is do the reaction in reverse. So if you remember, the new alkene that forms is always between 2 alkenes of the diene. So start to break this bond. Okay, so this is one of the new sigma bonds that would have formed. This one then comes over, and this one goes back to form the original dienophile. Usually when we do retrosynthetic reactions, we use an arrow that has 2 lines in it to say that that's a reverse direction, not a forward direction. And so if I'm going to look at that, I've got my diene, and then I have my dienophile. That's going to be a Z-dienophile, because in the product they were both on the same side, so they both need to be on the same side in the dienophile.